Hello everyone, welcome back to my channel. In this video, we are going to explore secure coding concepts using a real-world vulnerability as an example, that is Citrix Bleed 2. We will talk about memory safety, variable initialization, and how a small coding mistake can lead to a major security issue. Let's get started then. So here's what you will learn in this video. We are going to start our video by introducing the Citrix Bleed 2 vulnerability. We are going to use this vulnerability as a reference point in our video to discuss about secure coding practices. Then, since this vulnerability has uninitialized variable at the heart of it, uninitialized variable is the root cause of this Citrix Bleed 2 vulnerability, which was categorized as buffer overread. So we will look at initialized and uninitialized variables, how memory is handled in low-level languages like C and high-level languages like Python, Java. And then we will discuss how missing initialization can lead to sensitive data leak. So before we jump into secure coding concepts, let's first understand the real-world vulnerability that we are using as a reference point in this video. This is Citrix Bleed 2. It is officially tracked as CVE-2025-5777 in the National Vulnerability Database of the US, which is maintained by NIST. And it's a serious memory exposure flaw that was discovered recently in Citrix NetScaler's authentication handler. Citrix NetScaler is a device that provides remote access VPN services, load balancing to organizations. And now what makes this interesting is how little effort is needed from the attacker side to trigger this vulnerability. All the attacker needs to do is send a crafted HTTP post request to the endpoint authentication handler of the Citrix NetScaler device, which is authentication.do, and that's it. The authentication handler then mishandles that request and starts leaking old memory data like session tokens and session cookies to the attacker. All right, let's get started then. Let's understand how an uninitialized variable is the technical root of this Citrix Bleed 2 vulnerability. Let's, on the next slide, try to chain the memory management with variables and variables with uninitialized variables and uninitialized variables with this Citrix Bleed 2 vulnerability. Before we dive into the programming concepts, let me show you how all of this connects to the Citrix Bleed 2 vulnerability. It all starts with memory management. In languages like C and C++, memory management is not automatic. The programmer has to do it manually. Because of this, variables in C aren't automatically initialized like they are in safer high-level languages. And when a variable is left uninitialized, it might contain leftover memory content from previous operations. Now, if the program accidentally sends this uninitialized data back to the client, it can result in information disclosure vulnerability. And that's exactly what happened in this case of Citrix Bleed 2. A simple coding oversight led to a serious memory leak. So this slide is just to help you to visualize how these programming basics, memory, variables, and initialization that we are discussing are all chained together and how they ultimately lead to a vulnerability. All right, now let's start at the beginning by discussing the memory management on the next slide. All right, let's start our deep dive with memory management, one of the foundational concepts that directly impacts the vulnerability we are studying. In programming, when we create variables or objects, we need space in memory to store their data. Now, how that memory is managed, how it's allocated, how it's used and cleaned up can differ a lot depending on the language you use. In C and C++, which are low-level languages, memory management is manual. That means the programmer is responsible for allocating memory and also for cleaning it up when it's no longer needed. And if the developer forgets to initialize memory or clear it properly, the system won't help it. That's how uninitialized variables and memory leaks happen. On the other hand, higher level languages such as Python, Java, they handle memory automatically for you. When you create a variable in Python or Java, the language runtime ensures that the memory is initialized usually to null or zero so that you don't accidentally leak old data. What do you mean by null or zero or initializing the memory? Don't worry about these concepts. We will discuss them in detail on the next slides. For now, just understand that in higher level languages such as Python and Java, the memory management is automatic, it's initialized, and bugs like buffer overread and Citrix Bleed type vulnerabilities, they don't exist so often in Python and Java. But since the memory management is automatic in higher level languages like Python and Java, that makes the development easier and safer, but at the same time, there is a trade-off. These high level languages are also slow and less efficient when it comes to low level system operations. And that's where low level languages such as C and C++ still shine. Despite the risks, C and C++ are still widely used today in critical areas where speed, performance, and direct hardware access are non-negotiable, like in operating systems, network appliances, embedded devices, firmware, or even performance-intensive services like load balancers and traffic shapers. So, when you watch Netflix or when you're streaming something on Amazon Prime, the content delivery networks, their devices, when they are streaming the content to you, their code is going to run in C and C++ kind of low level languages because their speed and performance is very, very important. And in fact, products like Citrix NetScaler, where this vulnerability occurred, are also built using C or C++ for exactly the same reason, because you need to deliver speed and performance there. So you simply can't replace these languages in such use cases with higher level languages like Python or Java without sacrificing performance or control. So what we have learned on this slide is that while memory management in C, C++ introduces risks, it also gives what these languages require, that is power. And that's why understanding how memory works in C, C++ is crucial if we want to fully understand how vulnerabilities like Citrix Bleed to emerge. So with this understanding now, let's move on to the next key concept, that is variables and the two possible states a variable can have. So for now on this slide, if it was overwhelming for you, too much information, then just remember that in C, C++, memory management is manual, and that's why this causes some kind of problems, and this leads to the vulnerability that we are discussing. On the next slides, as you move ahead, you will form this comprehensive understanding of how all this fits. So just bear with me for a few more minutes and a couple of more slides, and this will all make sense to you. So now that we have looked at how memory is managed, let's talk about something that sits right on top of it: variables. In programming, a variable is simply a named container for storing data in memory. You can think of it like a labeled box where a program can temporarily store some information that it needs to work with later. For example, if you want to store a user's login ID, you create a variable called login ID. This variable will then hold whatever value the user provides, like Simon123 or admin123 or test user, whatever is the login ID of the user. And in the code on the right hand side here, I'm showing you the code of a program that is used for storing a user's login ID and how a variable can be used to hold that login information in the memory. So char login ID 256, char is the data type, login ID is the variable name, 256 bytes is the size of the memory that is reserved for this variable. So here we declared a variable named login ID that can hold up to 256 characters, but we are not leaving it empty. We are also initializing it. That means we are assigning it a starting value, in this case null, which is a placeholder that acts like a clean state. Why assign this null value? Why initialize the variable? Because the memory space assigned to that variable might still hold old junk data from previous tasks. So if we don't clean it first, unexpected values could be used or leaked later. So now when a real user logs in and enters his user ID like Simon123, that placeholder null gets safely overwritten with the new input that the user has provided. But here's something important. Not all variables are initialized. In some programs, a developer might declare a variable that is request memory for it, but forget to give it a starting value like null. And in that case, then that variable is called as uninitialized variable. So initialization means assigning a value right after the variable is declared. Uninitialization means no value is assigned. So whatever is already there in the memory space, that stays there. And that leads to unexpected bugs and security issues, because in that case the variable is in an uninitialized state and it might contain unpredictable data from previous memory use, and this can lead to unexpected behavior, and in some cases serious security vulnerabilities like Citrix Bleed can arise. So on the next slide, we will explore these two states of variable in more detail, that is uninitialized and initialized state in more detail, so you clearly understand the technical root of the Citrix Bleed 2 vulnerability. That's all on this slide. See you in the next one. Let's now talk about the two possible states in which a variable can exist: initialized and uninitialized. To make this easier to understand, I will give you a real world analogy. Imagine you are checking into a hotel. Now, ideally, before you enter your room, the hotel staff cleans the room, removes anything the previous guests have left behind, they replace the bed sheets, reset everything to a neutral, safe, clean state, right? But imagine what if they didn't clean the room before handing it to you? You walk in and you find someone else's leftover luggage, food containers, or personal belongings. So the room now is messy, it's unpredictable, and even potentially dangerous for you. That's exactly what happens with uninitialized variables in programming. When a variable is initialized, it means the memory space reserved for that variable is cleaned up and assigned a placeholder value like 0 or null, something that marks it as ready to be safely used. So when valid user data comes in, like a login ID, it simply overwrites this placeholder value and everything works as expected. But when a variable is uninitialized, no value is assigned at all to it, then it means that whatever junk data existed in that memory location from earlier operations, it stays there. And if the program reads from that variable or sends it back as a response, that leftover memory, possibly some sensitive information, can be accidentally exposed. So in this slide, you see both cases visually. On the left hand side, you see initialized variable that is safely set to null, like a freshly cleaned room. And on the right hand side, you see the uninitialized variable example that still holds this 0xA3 value that is left over from a prior use. And that's how memory leaks and security vulnerabilities like Citrix Bleed 2 can happen. On the next slide, then, we will go deeper into this concept and show how uninitialized variables directly lead to leakage and how attackers can take advantage of it. Okay, so now that we have understood what uninitialized variables are, let's look at why they are dangerous, especially in the context of low-level languages like C and C++. So when a variable is declared and not initialized explicitly, the memory it occupies may contain some leftover data from previous operations. This is what we discussed on the previous slide. And this residual data, also known as garbage value, can accidentally get processed or even sent out in responses by the server to the client if the program code isn't careful about it. And in a security context, this is very critical because if the variable is part of a server's user authentication handling logic, Then, imagine the server might unknowingly leak old memory contents to the client. And depending on what's left in the memory, this could also include sensitive user data, session tokens, or other application level secrets. And this was exactly the problem in the Citrix Bleed vulnerability. An uninitialized variable, uninitialized buffer, when used in forming the server's response, it caused the server to leak out unintended memory contents to the client. Not because the server was hacked or the logic was bypassed, but simply because a variable in the code of its authentication handler endpoint wasn't initialized properly before use. And by initialization, as we saw on the previous slide, meaning it was not given a value, a placeholder value like null or zero. Just like we talked about this hotel analogy, like not cleaning the room before assigning it to the guest. So that's all on this slide. In the next slide, we will take our understanding of uninitialized variables a step further, because uninitialized variables are at the technical root of the Citrix Bleed vulnerability. So in next few slides, we will look at two specific scenarios that will illustrate to us how variable initialization or the lack of variable initialization can determine the outcome of a request. So that's all on this slide. See you in the next one. Now that we have seen how uninitialized variables can pose serious risks, let's explore this further through two practical scenarios. In both cases, let's assume that the variable on the server is uninitialized, meaning it might contain leftover data from memory. In scenario 1, we will see how the system behaves when a legitimate authorized user sends a properly formed request to the server. And in scenario 2, we will see what happens when an attacker sends a malformed request that is missing with expected inputs to a server that is having this uninitialized variable problem. So, what will be the outcome of the server? What will be the response of the server? We will see that, how it differs in both cases. So these two scenarios will help us clearly understand how the server behaves based on the presence or absence of the user input, and then why initialization is critical to prevent data leakage. All right, then let's explore these use cases in the next slide. All right, let's walk through scenario 1. Here we are looking at a typical case where a user sends a login request to the server, and the request includes the login ID parameter. For example, something like login ID equals to Simon123. Now, it's important to note that it doesn't really matter if this is a valid login ID or not. What matters is that the user has provided some value to this login ID parameter. The user has not left this login ID field empty. So, even if it's an invalid username or incorrect username or maybe some random string, string of letters, what is important is that some input is provided in the request by the user to the server. So in step 1, the user sends this input to the server. In step 2, the server receives this input and starts preparing the variable in memory. At this point, the memory location for login ID might still have leftover data from a previous request. This is the uninitialized state. Maybe it contains a random value like 0xA3 from previous operations. Since this is an uninitialized variable, it is not initialized, meaning there is no placeholder like null or zero assigned to this variable. So whatever is there in the previous operation, that is, that those content are still lying in that memory region. So now comes the step 3. Since the user gave an input, the server can safely overwrite that memory location with the new value. And in this case, Simon123 was given by the user, so this is where things are safe. The old memory content gets written with the new value that was provided by the user. Now in step 4, the server uses that freshly written value to generate a response. It might prepare a session token or some login related output. If the login ID is right, then the server will give the actual valid token to the user for that author with that authorized session. If the login ID is incorrect, the server might give some kind of login related output, maybe some error or something else. But the important thing is that the input was provided by the user, some value was given to the server to work with, so the server was able to process this request normally. And then in step 5, the server sent the response back to the user. Since the memory was properly overwritten with the user input, there is no risk of exposing old or leftover content from the memory. So all is good, life's good here. The big takeaway here from this scenario 1 is that as long as the user sends some input, even if it's incorrect, the server has some input to work with. It will then override the memory with that new input and the situation remains safe. The problem doesn't arise from invalid input. It arises when there is no input provided at all in the login information. When login ID is left as blank and sent to the server. That is where then the server does not have some input to work with, and that is where the real problem starts because of this uninitialized variable that we will explore in scenario 2. Now let's look at scenario 2, which is where things get risky. This time the request is a bit different. The attacker sends a login request but leaves the login ID parameter completely blank. So it looks like this. Login ID equals to empty, missing parameter, no value at all. So in step 1, this empty request reaches the server. In step 2, the server receives the request but doesn't perform any check for the missing parameter. It goes ahead and starts processing the response. But here's the catch. Since there was no actual value provided for login ID, the server has nothing to override the memory with. Now look at this before state. The login ID variable has already been declared. Character login ID 256 carries the data type. Login ID is the variable name. 256 bytes is the size of this memory region that was allocated to this variable. That means the memory allocated for this variable, since it was not initialized, it holds whatever leftover data was sitting there before, maybe from a previous user session. So I'm showing it as 0xA3 here, just some random old byte. Then in step 3, because no input was provided, the memory remains unchanged. Nothing overwrites it. Then in step 4, the server sends a response, and this is where the problem happens. The response may now include this stale-over value from the memory, exposing session data, tokens, or other sensitive content from an earlier use. So the key difference here is simple. In scenario 1, the memory got cleaned and overwritten with user input in this step 3. But in scenario 2, in this step 3, since no input was provided, the memory stays dirty, leftover, and that leftover content accidentally makes its way into the response that is sent back to the attacker. So this is the heart of the Citrix Bleed 2 vulnerability. The server didn't proactively initialize the variable, and it didn't validate that a required input was missing. That's why memory leakage occurred. So that's all on this slide. In the next slide, then we will talk about the mitigation for this and how it can help in these scenarios. Now that we have seen how missing input can lead to memory leakage, let's talk about how we can mitigate this risk. The answer is pretty simple: proactive initialization, but it's super effective. Here's what it means. The moment a variable is created, we assign it with a safe default value like 0 or null or even an empty string. This happens after the memory is allocated. Now in higher level languages like Java, Python, this is automatically taken care by the operating system during runtime. But in lower level languages like C and C++, you have to do it manually by writing a code for it. And why is that important? Because it ensures that the memory isn't holding on to any leftover junk from earlier operations. And how does this actually help? When the input is missing from the client side, like in our attacker scenario that we were seeing on the previous slide, then the system won't respond with stale memory. Instead, it will respond with the placeholder value like null or zero or some empty string that was proactively assigned to this memory region when this variable was created, because you declared that in the code. And this completely then blocks the memory leak path that we saw earlier. And you can see in the graphic here that as soon as the variable login ID is declared, it's assigned with a safe default like 0 or null. That means when the response is prepared, no garbage data gets exposed, even if the user didn't send any input. So this is exactly what didn't happen in Citrix Bleed 2. And that's why this simple habit of proactive initialization can go a long way in securing your applications. Now, let's take our understanding about this mitigation step a further by replaying the scenario 2 for the attacker request on the next slide. How proactively initializing variables can help prevent data leaks from memory. Now let's replay the scenario 2. Let's take a look at how this mitigation changes the outcome when the same attacker sends a blank login ID again. So we are replaying the scenario 2, but this time the outcome will be different because we have applied the mitigation of initializing the variable to a safe default value like 0 or null. So step 1, the attacker sends a post request to the login endpoint to the server, but leaves the login field empty, no input provided, just like before. And then the server receives this empty input just like before, but this time something important has changed under the hood. Here the variable is initialized with a safe default value, and that is the critical part. Step 3 is very critical here. Earlier, this is where the problem happened in scenario 2, where when no input was provided by the attacker, that meant no overwriting of the earlier memory. And then the server accidentally used leftover memory content in its response, and that could have leaked session tokens or other sensitive data. But now, since the variable is initialized with these values, even though no input has been received from the attacker side, the variable login ID will not have any problems because it was already initialized at the time of memory allocation. That means instead of containing garbage or leftover content, the memory reserved for the variable now is holding a clean, safe default such as null or 0. So even though the server has nothing to write here, at the same time, it also does not have to deal with old unsafe data anymore. It will simply proceed using the already initialized safe value in its response. And as a result, then the server sends out a clean response that contains only the safe default. No memory leak, no exposure, no risk. So even though the attacker sent the same blank input, this time the vulnerability is closed. And that's the power of proactive initialization. The safest value is already in place before anything ever gets processed. This is like that hotel room analogy where the room is already cleaned before the guest is assigned with the room. All right, then I hope you have gotten a sense of what this vulnerability is about. In further sections, we will break down this vulnerability with more examples and more technical details. All right, then. Thank you. That's all on this slide. All right, that's the end of section 2. Let's wrap up section 2 with a quick summary of what we have learned so far. So we began our section 2 by chaining the root cause, showing how the Citrix Bleed 2 is rooted in basic programming concepts, memory management, variable usage, and initialization. And then we started our section 2 by learning about manual memory management in C and C++, how in higher level languages like Python and Java, memory management is automatic, but in C, C++, developers have to explicitly handle this. It's a manual process, or they have to face potential security issues. Then we took a look at variables. What are variables? We understood that variable is simply a named space in memory that is used to store some information, like a user's login ID. And then we discussed the concept of initialization, which means assigning a known value such as null or zero or a placeholder to that variable's memory. Then we talked about uninitialized variables, which occur when memory is allocated but no value is assigned. In such cases, then the memory may still hold leftover data from previous operations, and that might accidentally leak sensitive information to the attackers. And then we explored the dangers of uninitialization through two practical scenarios. In scenario one, everything worked safely because the authorized user was providing a valid input, and more importantly, a input was provided. Whether it was valid or invalid doesn't matter, but if an input is provided, the old memory still gets overwritten, and it's a safe scenario. But we discussed scenario 2 as well, where we saw how sending a blank input could trigger a memory leak. And then we discussed the mitigation, that is proactive initialization of variables when they are created. And we replayed the scenario 2 to show how the outcome would be different if there is proactive initialization as a mitigation applied to this vulnerability. Alright, thank you for watching. This was a carved out version of a full 1.5 hour video that I have on Citrix Bleed 2 on my YouTube channel. This video was carved out specifically for people having application security and coding knowledge. The full 1.5 hour video uses some simple real world analogy and covers some more basics for people who are not having knowledge on coding and application security. And if you're interested for the full 1.5 hour deep dive on Citrix Bleed 2, you can find that on my channel. Thank you.